morning, friends. Let's talk about linked list. Okay. First of all, before talking about linked list, let's talk about dynamic memory allocation. So, okay, the mechanism by which storage of memory cell can be allocated to variables during runtime is called dynamic memory allocation. Mostly, we will not use this still now. While doing programming, we will always allocate the memory statically. But there is a vast scope for dynamic memory allocation. Dynamic memory allocation is the allocation of memory during runtime. Okay. Static memory allocation can only be done on the stack, whereas dynamic memory allocation can be done on both stack and heap. So it uses mainly heap, but sometimes it uses stack also. An example of dynamic memory allocation to be done on the stack is recursion, where the function are put into called stack in order of their occurrence and popped off one by one on reaching the base case. Okay, so this already you know. Yeah, when we suppose we are calling a function. Suppose I'm calling a function factorial. Let's take notepad. Okay, I'm going to call factorial function factor of 5. So this function, actually we know the code, factorial of n equal to is if n is less than or equal to 1, return 1, else return n into factor n minus 1. So this is the code actually, you all know about this into fact. So this is a function. So whenever I'm calling a function factorial of 5, I want to perform factorial of 5, what happens is that we want to we'll check the condition n equal to n is less than, it's not n less than or equal to 1. So this condition should execute. So we are going to call 5 into factorial of 4. That is factorial of 4 should be called. At this point, what happens to factorial of 5 program? Okay, so some memory will be allotted for executing this program. So that information will be stored in the stack. For that purpose, we use that will be allocated dynamically. Okay. So for that, we use actually this stack. Normally, what we can say is for static memory allocation, we use stack, and for dynamic memory allocation, we use heap. But in this particular case, we use stack for dynamic memory allocation. By allocating memory on the heap, we need to delete the memory manually as memory is not freed by the compiler itself, even if the scope of allocated memory finishes. This is one of the important points. When we are implementing something in dynamic memory, we have to free it. Because what we do is we will simply create a memory, we will complete the execution, is stopped. At that time, compiler will automatically delete all the memory blocks. But in the case of dynamic memory allocation, it will never happen. So we have to allocate, we have to deallocate it. There are certain functions for deallocating the memory. Okay, let's talk about array and linked list. So array is a data structure where elements are stored in consecutive memory locations. Okay. In most cases, array are static as we allocate memory beforehand. In those cases, once a memory is allocated, it cannot be extended. So we can extend it. We can use dynamic memory allocation, but mostly we'll never use that. We use only arrays. Array is a static memory allocation. Okay. So size will be fixed. So if you want to deallocate, if you want to dynamically allocate the memory, also suppose we will say, okay, we can use dynamic memory allocation for array also. But there what happens is that memory will be allocated initially. If you want more space, it will be that whole memory space will be deallocated to some other locations. So I'll show you an example. Okay, I'm allocating a memory. Suppose I'm allocating a memory. Okay. Of 3 blocks has been allocated. After, okay, I need to store 4th element. It will not be allocated here because this is a continuous memory space and there is a chance that this memory is not free. Okay, so what we will do is when we are reallocating the memory, create another memory block and we will allocate the memory separately. Like the whole thing will be copied to the new memory block. So that's the option of an array. But when we are talking about linked list, so linked list is a dynamic data structure. In linked list, adjacent elements are maintained by links or pointers. So this is totally a different thing. We are going to allocate memory in different places, and these memory locations will be connected because we have to connect the elements. Okay, using some address. Okay, so the linked list is adjacent between elements are maintained by links or pointers. So it will use pointers to allocate them. One of the main factor is that it's not consecutive. The array is consecutive in allocation, but here there is no continuous memory. Okay, so what is in these self-referential structures? Self-referential structures are those structures that have one or more pointers which point to the same type of structure as their member. So that is called as self-referential structures. So it's let's see this example. Struct node. Int data is there. Struct node starling. When you see this pointer is actually pointing to the node itself. Its type is node, and this point is a pointer, and this pointer is pointing to this. That is called self-referential structures. Self-referential structures are those structures that have one or more pointers. Here only one pointer, which point to the same type of the structure. Okay, as the structure. So such type of structures are called self-referential structures. So we will be using these self-referential structures a lot in the case of linked list. Okay. So let's examine what is a linked list is and how it looks like. I said linked list is a collection where elements are stored continuously. We will be storing different locations. So we have to see the structure. Okay. Linked lists have a data. They have a data actual content and a link address of the next data. That's the structure of the linked list. So it will be a memory location. That memory location should have at least one data field and a link field. Elements in the linked list are called nodes. Okay. Another important point. This is called a node, which contain data and the link. Data can be of any number. Okay, here I am saying okay one data. It can have any number of data, but it should have a link that contain the address of the next memory block. Okay, that is linked list. Linked list is an ordered collection of finite homogeneous elements, data elements. You can say heterogeneous also, but it's homogeneous in the sense it can store only similar type of elements. It's not like that, but mostly it is homogeneous. So it's a homogeneous data elements because once we create a structure, elements in the structure will be same. We can store in that node, that memory location, we can have any number of type, any type. What mean is that if I created an integer variable inside the structure, I cannot store a character inside that. For that I have to create another. So it's a homogeneous data elements called nodes where the linear order is maintained by links. In the case of array, the linear order is maintained by consecutive memory locations. But here it is not continuous. Memory will be stored in different locations, and the connections or order will be kept by having a link. Depending upon the link required, linked lists are classified into single linked list, double linked list, circular linked list. So these are the three common linked lists that we are going to study: single linked list, double linked list, and circular linked list. So I think it's clear what is linked list. So linked list is a homogeneous data elements. It's a collection of homogeneous data elements called nodes, and these nodes have been interconnected using links. That's it. So this is a typical structure of a linked list. In a singly linked list, each node contain only one link. I told you there are different type of linked lists is there. So mostly what we use is a singly linked list where the elements have only one link. Only one link will be there. It's point to the consecutive nodes in the list. So header will be there. It will be pointing to what is header? I will say it's a node. First node will be connected to another node. This node will be connected to another node. This node will be connected to another node. And this is actually 64 is connected to 14. 14 is connected to 72. 72 is connected to 80. And 80 is not connected to any other. So this is the structure of a list. Okay. We are going to briefly see what are the contents. Here N1, N2 and up to N6 are nodes in the list. N1, N2, N3, N4, N5 and N6 are the nodes in the list. Header is an empty node having data content null. Another important word, field, header. It's a node where the data part is empty. This portion is empty. That's called header. And only used to store the address of the first node. So it's a special type of node where the data field will be null, and this node is used to store the address of the first node. Here the first node is N1 and this header node will have the address of N. If header node link is null, then linked list is empty. Another important factor. Okay, if this header is not pointing to any place, okay, then that means the linked list is empty. Very simple. If we know the address of the header node, from the header node link we can trace the next node and so. Okay. This is another requirement. What is this? Is one of the requirement of single linked list. We have to know the address of the header node. If we know the address of the header node, what we can see is from the header node we can get the address of the first node. From the first node we will get the address of the next node. From second node we will get the address of the third node. From third node we will get the address of the fourth node. From fourth node we will get the address of the node. And finally from fifth node we will get the last node address. So it is interconnected. So only requirement we have is we should know the address of the header node. Header node. Okay. Last node link field will be null. Another important factor. How will you identify the last of the link list? It is a collection of memory locations. So last node link will be null. So it's link. It's null. It's null. Okay, single linked list can move from left to right only one linked list. So another important thing, we cannot go back. So direction is only one way. Okay, that's a single linked list. So this is structure. Here we are not using the header node because header node is just a memory location. It stores the address of the first node. So instead of a header node, we can use a header pointer that we are using here. Linked list represents using free pool of an important thing. Representation of linked list. How will you represent this? Okay, linked list is represented using free pool of storage. This method, there is a memory bank, memory manager, and a garbage collector. Okay. During the creation of linked list, whenever a node is required, a request is placed to the memory manager. Okay, I will need some memory. I will request the memory manager to give that memory. Okay, the memory manager will search the memory bank. So we'll have a memory bank will be there for the block requested. And if found, grant the desired block to the call. Okay. Whenever a node is no more in use, the garbage collector will return the memory to the memory bank. Okay, this is the process. This type of memory management is known as dynamic memory management. So important. So it's like this. So we have nodes are there. I require a new node. This node require a, this is the last node want to create a new node. It will request the memory manager. Memory manager will see the memory bank. Okay. Okay, we have some space should be there. Is there. So what it will do, it will allocate the new block and it will use this XY as that block is been allocated to this. So after using this, the garbage collector will deallocate this. It's the structure of a. Okay. Another important thing, operations on linked list will say, okay, so linked list structure will be like this. Node will be there. Node will have a value, can have a number of values, and a single link. Okay, here node is a special node which is used to keep track of the entire linked list. Already said that. Initial case head node is set to null like. So initially head node will be set as null. So another function we are going to use for implementing. Create node is a function that will create a node and return the address location. So we are making some assumptions for studying about the operations of linked list. First assumption is we will have a node structure. Whenever the node structure is been called, it will allocate a memory block like this. For allocating the memory, we use a function called create node that will allocate the memory. So how much space it will be allocated? It will allocate a space for a value. Okay, we can store a value there and a link. Then we said, okay, initially we will have head node will be there. Head node is a node containing the address of the first node's address. Okay, so initially the head node will be set as node. That's the requirement. So this is the structure. So operation we will see in the next class.